I would like to introduce Dr. Morgan Abney, who is the ECLIS Technical Fellow in the NASA Engineering and Safety Center at Marshall Space Flight Center, and she'll be talking to us about life support and thermal management challenges in space, lunar versus LEO. So welcome, Morgan.
Good morning. Thank you so much for having me this morning. So as Kevin mentioned, today I'm going to be talking a little bit about life support and the thermal management challenges that we have in space, and really as a comparison between what we've learned and what we know from low Earth orbit and space station versus the things we learned from Apollo, and then the unexpected that we anticipate as we go to the South Pole. All right, next slide, please. All right, quick overview of what I'm going to talk about today. I'm going to give a basic overview in tabular format of lunar versus LEO environments, and then I'm going to go into a little bit more detail on those environments. So thermal environment, gravity, radiation, dust, and the internal cabin environment, and the challenges that each of those poses to our life support and our thermal control system. All right, next slide, please. All right, so this first slide is really here to try to show and compare some of the differences between ISS, what we learned from Apollo, and then what we're going to see on the South Pole. So of course, the location is a key factor when we look at different environments. For ISS, of course, we're in low Earth orbit. Apollo was lunar equatorial, so from about 9 degrees south to about 26 degrees north. And I've got a neat graphic coming up that gives a visual of this. And then, of course, the lunar South Pole, where we're looking at 84 to about 90 degrees south. The next consideration is the thermal environment. So on ISS, of course, we have that solar flux coming from the sun, and then we have this great deep space sink that we can utilize. For Apollo, we have, of course, similar solar flux. We know that, at the equator, we get to near equilibrium at the surface from the solar flux, and that the incidence angle really drives those thermal conditions, that direct light from the sun. And then we have that 27-day revolution that plays into the thermal environment. Now, for the lunar South Pole, it's a little bit different because of that incident angle. The topography of the surface really starts to drive the thermal conditions. And I think that the graphic on the next page is going to help show that a little bit better. Now for gravity, we have ISS, of course, is microgravity, free fall. And when we go to the lunar surface, we have that one fixed gravity. And for life support systems, that's challenging for certain reasons, but it's also a big benefit for other reasons. And we'll talk a little bit about that. The radiation on ISS, we have the great benefit of Earth's magnetic fields, radiation belts that are able to help protect the folks on space station as well as our equipment. But on the moon, no natural protection. And I say that, and of course I caveat it with the potential protection that we get near the full moon as the moon goes through Earth's magnetic fields. But I'm going to talk a little bit about a recent paper that I read that suggests that there may be some challenges even there. And without going into too much detail now, the next one is dust, and I know that's a big topic here at this lunar surface science workshop. And so I'm not going to go into a lot of detail on this, but when we think about ISS, we know that we get intermittent orbital debris on the outside of ISS that would affect performance. But internal to the cabin, we get sources from the ground and whatever we generate inside the cabin. With the lunar surface, of course, we have the same sources generated from the ground and generated in the cabin, but now the big concern is regolith. And we're going to talk about that a lot over the next day and a half. And then lastly, the cabin environment. For space station, of course, this is variable within a band, but approximately 14.7 psi and 21% oxygen, trying to be similar to Earth as we were able to get up there. For Apollo, we had 5 psi absolute cabin environment pressure and 100% oxygen. But as we go to the lunar South Pole, when we anticipate much more EVA activity, we want to drop that down and get pressures 10.2 and 8.2, which requires higher percent oxygen, so 26.5, 34% oxygen. And so that adds new challenges to how we design the system. And we'll talk a little bit about that as well. All right, next slide, please. All right, so this graphic shows, of course, the moon and the different locations of where Apollo landed. Each of those green triangles that you see was one of the Apollo landing sites. And as you can see, they're all approximately near the equator. And so when we landed there and we were designing our thermal systems, we had the direct sunlight, an angle of incidence about 0%, with a max solar irradiance of between 1,200 and 1,400 watts per meter squared. So our delta temperature from noon to midnight here, referring to full light versus full dark, is about 290 Kelvin, and we end up with an average min and max temperature, approximately 92 Kelvin at the min, and then almost 400 Kelvin at the maximum. And so we know how to design these systems, and we were able to demonstrate them over the periods of time that the Apollo missions were on the surface. As we go to the South Pole, our angle of incidence is approximately 90 degrees. And so now you don't have that direct sunlight. And as I mentioned before, the topography on the surface starts to play a lot bigger role on how much sun you get and the different thermal environments that you're trying to design to. So your max solar radiance there is now less than 250 watts per meter squared, with a delta temperature of about 120 K from noon to midnight, and much lower average maximum temperatures of about 185 K. So of course, all of these things are going to play into how we're designing our systems as we go to that South Pole. Next slide, please. There you go. So this slide is showing comparison of the topography at the South Pole versus the surface temperatures. I pulled these two images, I just loved them, from the papers you see there, Glasser and Page. And on the left, what it's showing is the different topography. This is right at the South Pole. That's the Shackleton crater there on the right. And so you can see a delta of about 5 kilometers from the lowest to the highest point in this image. And so a lot of variability. But you also see there that what's shown in the image as a shadow is an area which is going to be in shadow if the crew were to land there, to operate there. And so on the right, it shows the temperatures, the temperature deltas within a very specific time band here. But it really shows the variability that you can get in a very small area due to the topography. And so on this image, you're seeing everything from 25 Kelvin all the way up to 300 Kelvin in this 50 by 50 kilometer area. And so we can take advantage of that by where we're placing our lander, where we're doing our missions. But it also introduces significant challenges when you have temperature variations over relatively short distances between 25 and 300 Kelvin. Next slide, please. All right, so what does this mean for how we're designing our life support and our vehicle thermal systems? Well, first, both the passive and the active thermal vehicle design is going to be affected by the significantly reduced solar flux at the South Pole. And so maintaining our vehicle and our hardware viability during prolonged period of darkness is going to require active thermal control, heating in particular. This will prove more challenging with limited or no power if we're relying on solar power. The minimum temperature at the South Pole is low enough to freeze nitrogen and oxygen. And so from a life support perspective, we have to maintain temperatures or have systems in place that are protecting the systems from freezing up. And also, if we intend to store water, we have to keep above 273 Kelvin so we're not freezing those. And then when we consider spacesuits, the materials have to be carefully designed to protect the crew against significantly lower temperatures and prolonged lower temperatures than we saw at the equator. And in the event of falls where the crew might contact the ground, now you have a risk of conduction. What does this mean for the design of our spacesuits? It's something we have to consider. Next slide, please. So gravity is the next environmental condition that we consider. On space station, we had this free fall, and now we go to the surface of the moon, and we have this 1/6 gravity that we need to deal with. Next slide, please. So now gravity has both challenges and benefits for us. Some of the big challenges, first is fire. We have very limited data on on the behavior of fire and partial gravity. I know Gary and other folks are going to talk about that at length later, so I'm not going to go into too much of that, but that's a significant challenge. For spacesuit design, for space station, we have suits that in microgravity don't require the crew to be able to bend down and walk around and twist and move all different ways. But once they get on the surface, the suits are going to be able to have to do that. And so the materials that we're making the suits out of have to be both durable and flexible. And we also have to consider mass. So right now, if we have a suit that's approximately 280 pounds on the surface of the Earth, that's effectively 47 pounds on the surface of the moon. That's a lot for a crew member to carry around for 6 to 8 hours a day during an EVA. And so if we go heavier than that, right, that becomes a major concern. And it's a lot more difficult to reduce mass on the little tiny life support system. So that becomes a challenge. And then also the mass of our systems. So for mission concepts where we anticipate starting with maybe a bare bones life support system, and then over time, advancing that system, adding new technology to further close the loop, for example, we really have to consider what that means for mass when they try to integrate or install that hardware. Just an example, if we have an oxygen generator that's about 1,500 pounds on Earth, on the surface of the moon, you're looking at 250 pounds. It's not that big a deal as far as weight's concerned for ISS to be able to install that, right? It gets tricky with having to maneuver it, but the weight isn't something that we have to think about on the surface of the moon. Now you have to have enough team members and whatever tools you're going to have to hoist a 250-pound oxygen generator into the vehicle and get it connected. As I mentioned, this is already challenging in certain ways in microgravity, but it's a whole different type of challenge when we get to the surface of the moon. There are benefits, though, for gravity for life support systems. In particular, any system that has multi-phase separation that we need to do is going to be easier on the surface of the moon because we get help, a little bit of an assist from gravity. A toilet hardware operation gets easier to use with the help of gravity because we're not having to fight the free fall. And then loose items, water droplets, loft stocks, those all settle out rather than finding their way to vents and electronics. And so this could potentially help us as we're designing these systems. Next slide, please. Now, radiation. So on the surface of the moon, we do have localized low-level magnetic fields on the lunar surface, but those offer limited protection, really only limited protection when you're in areas where those are available. But you still have solar particle events coming at you. The angle of incidence is going to help, but we still have to be able to shield for those. And of course, galactic cosmic radiation is always an issue. Now, in doing some of the research for this talk, I was reading some older papers about radiation and potential protection of the moon. As the moon goes through our magnetic fields of the Earth, that we get potentially some protection from those. But last year there was a paper that was published, shown there by Shang, Tang, and Shi, that suggests that the magnetotail that you see in the picture here on the right, as radiation is hitting our magnetic field and those field lines are breaking apart and reforming, that you end up almost getting like a windsock effect at the back side of this. And so that magnetotail is whipping around, and then potentially you're getting worse radiation at certain parts of the moon because of that effect. And so what does that mean for how we design the systems and how we protect and the level of radiation that we're protecting against? So there's an ongoing consideration. Next slide, please. So the challenges to the life support system, of course, crew protection is a big part of this during habitation. So we need the general vehicle to provide some level of shielding. We probably have to provide a safe haven for events that, solar particle events, where the crew has to protect themselves, and then also crew quarters where they're sleeping every night. The picture on the right here is a picture of the ISS crew quarters. And it has a certain level of radiation shielding, but of course, as we go to the moon and we don't have all the extra protection that ISS has, we're going to have to add additional support probably for them. Also, crew protection during EVA, shielding for the suit, and then also space weather forecasting. We have to be able to give the crew a heads up that something's happening with enough time for them to get into their safe place or to take cover. And then effects of radiation on food and medicine. Now, for really short-term short-term missions, this is probably not as big of a deal, but as the last talk was speaking to, part of this is preparing for Mars, and Mars are much longer duration. And so we need to understand how radiation is affecting our food and affecting our medicine, and be able to accommodate and protect those resources. Next slide, please. Now, dust challenges. Of course, again, this is a big topic. I found that picture on the right of Gene, Apollo 17, and you can see all the dust on his forehead and on the suit. And you can just imagine how much effort it's going to be to clean that up and make sure that it's not getting into lungs and into systems. So vehicle thermal challenges, there's the question of what happens when we get dust on our radiators or on our solar panels for that matter. What does that do to our performance, and how do we protect against that? Also, within the cabin challenges, general cabin cleanliness, crew health, for our atmosphere revitalization systems, our HEPA filters, and how are we sizing those? How are we accommodating additional dust in the cabin? What happens if it gets into our heat exchangers or our carbon dioxide removal systems or downstream of that? We have to understand those effects and also mitigate against them. And then the hardware, any hardware that has fans and air cooling, if we're blowing around dust inside the cabin, we need to understand the effects of that. And then for EVA challenges, the dust potentially introduces triboelectric charging effects as the crew is shuffling along the surface. There's also the concern of thermal effects for dust adhering to suit materials. What does that do to thermal protection? And then lastly, the durability of the suit materials. What are the abrasive effects of that dust? And because of the way that the pressure garment is designed, it's multi-layered. So what happens when dust gets in between those layers and gets deeper and deeper into the suit? At what point do we have a failure? How long do our systems last, and how do we make them to be more durable against that dust? Next slide, please. So the last area is cabin environment and challenges. I mentioned that for high frequency EVA operations, we want to go to a reduced pressure environment inside the cabin. This reduces the pre-breathe durations and reduces the risk for decompression sickness. But there are challenges with that. You're increasing the total oxygen in the cabin and lowering the pressure. So that increased oxygen increases our flammability risk. We need materials that are able to stand up to that. We also need systems that are able to control oxygen in a narrower bandwidth. The decreased pressure can will reduce the density of the air for cooling, so our existing systems would be less efficient. We're going to have to design those to accommodate that. And then the systems that reference ambient pressure for pressure control and venting, those are going to require redesign in order to maintain performance. I will mention there's an ongoing NASA Engineering Safety Center assessment looking at what the lower pressure, higher oxygen environment will do to what that will mean to our existing ISS designs and how we'll have to modify to be able to accommodate a lunar surface mission. Next slide, please. So in summary, there are significant known differences between our ISS environments and the lunar South Pole environments. And these differences, of course, are going to drive changes that we're going to have to make to the design of our life support and our thermal systems. We need a lot of data to be able to better characterize these environments. I think a lot of it's going to be talked during this event, particularly the dust, radiation, and other things. And so we need the data to better understand the effects of the environments on our systems so that we can best design them to accommodate the missions that we're going on. And that's my last, well, one more slide, please. I open up the floor to any questions folks have. Thanks so much.
Great. Thank you, Morgan. And we do have time for a couple of questions. We do have one on from Marshall Tabitha. Some important activities will have to occur in a radiation shield that is built. An example is plant growth. How will one assess the protective effects of the radiation shielding?
Yeah, I think that's probably a question for the folks who are designing those radiation shields. I know that there are people on the line who might be able to better answer that. I don't know, does anyone want to take that on? I personally don't have an answer for you.
Okay. Yeah, if you do have an answer, if you can just put it into the chat and answer to everyone, that would be great. And then the other question we have is from Paul Furcool. Do you have a rough idea of cooling heating levels required for an expected size lunar habitat during lunar night, noon and night?
So, gotcha. Yeah. So right now there are studies that are going on internal to NASA to try to quantify exactly what that is. We have existing documentation that exists out there. For example, the baseline values and baseline values and assumptions document that we use for the amount of heat that, for example, a crew member generates, how much our hardware systems generate, and so there are pretty well defined in-cabin numbers for that. There is also data that exists out there for existing radiators and those types of things. But as far as the habitat itself, it's going to be dependent on how it's designed, where it's sitting, particularly where it's located at the lunar South Pole. So there's a lot of TBDs in that. It's really based on the assumptions that you have.
Okay, great. Well, thank you, Morgan, for that great informative talk.